staff of the Engine Combustion Research Department at Sandia National Laboratories Combustion Research Facility in Livermore, California, where he's been since 1996. Charles is going to talk to us today. He's going to give us an introduction to ducted fuel injection systems.
Thank you very much for the introduction, Rob. I appreciate that, and it's great to be with you here today to talk to you a little bit about ducted fuel injection, which is a pretty neat new technology, I think, and I hope you will agree by the end of this talk. So before I get started, I'd like to gratefully acknowledge the support, financial support for this research from U.S. Department of Energy, Office of Vehicle Technologies. My program managers are Kevin Stork, Mike Weissmiller, and Gurpreet Singh. So our objective in this research is to maintain all the desirable attributes of conventional diesel combustion, and that schematic there is supposed to look like a truck wheel. I did my best in Illustrator. But so it has a lot of desirable attributes, of course, and so we'd like to maintain those, but we'd like to clean up the emissions tremendously, maybe 1 or 2 orders of magnitude lower soot and NOx simultaneously. And then for sustainability, we'd like to harness synergies with sustainable homegrown fuels. And I think this is a nice path forward for engines into the future. So how do we achieve this? Well, I'm going to explain that, and to explain it, what I'd like to do is go all the way back to just fundamentals of conventional diesel combustion. So we'll start there. So what is mixing-controlled compression ignition combustion? It is compression ignition combustion where ignition and the majority of the heat release happen while the fuel is being injected. That distinguishes it from, I think, the way a lot of this community has been going, which is toward more globally premix strategies. Mixing controlled compression ignition just has local premixing, not global premixing. So it's quite a bit different from HCCI, MCI, or PPCI, SI, LTC. Conventional diesel combustion is, of course, the classic example of mixing controlled compression ignition, but as you will see, there are other ways to do this. So for conventional diesel combustion, I'll go back to the very well-known conceptual model put forth by John Deck, and that's what you see here. You see fuel being injected. This is just one spray inside the combustion chamber, so fuel is being injected and charged gas is being entrained, and at a certain distance downstream, you get a standing premixed auto ignition zone. Near the axis of that fuel spray, you have fuel-rich conditions at high temperatures, and so pyrolysis reactions tend to produce soot. Around that rich region, you get a stoichiometric diffusion flame. That stoichiometric diffusion flame is hot, and on the lean side of that hot flame, there is nitrogen and there is oxygen. So you create nitrogen oxides. So this kind of gives you the origin of soot and NOx, and we'll come back to why that's important. So of course, conventional diesel combustion has a lot of advantages, and it also has one major disadvantage, which has limited, I think, its penetration into the market to this point. So it does have inherently high efficiency. It's very easy to control ignition timing by just controlling when you inject the fuel. There's a short ignition delay, and then your combustion happens. It has high torque and power density. It's durable, it's reliable, low hydrocarbon and carbon monoxide emissions, low cyclic variability, so it's drivable. It's fuel flexible. So it's got all these great attributes. Well, why doesn't everybody drive a diesel engine? Well, as you know, probably, the primary disadvantage has been this soot-NOx trade-off. So on the last slide, we saw where soot and NOx come from. Here's the soot-NOx trade-off. Basically, when you do something to lower soot, NOx goes up. When you do something to lower NOx, soot goes up. And you can't address them both at the same time. And so why is that? Really, it's because if you want to get rid of soot, you have to produce oxidizing conditions. And that's great for oxidizing soot, but it produces other oxides, like nitrogen oxide, right? And conversely, if you want to get rid of NOx, you want to go to chemically reducing conditions. But when you go to chemically reducing conditions, then you can't oxidize soot. So I would argue that as soon as you have soot and NOx inside the combustion chamber at the same time, you have lost the battle, at least in terms of you're going to require after treatment. So if an ounce of prevention is worth a pound of cure, what we want to do is prevent these emissions from being formed in the first place. So because we can't prevent them both from being formed, I don't think, maybe at least we can prevent one from being formed. And because we want high efficiency, high combustion efficiency, it seems reasonable to try to minimize soot formation. And so that's been our approach. Knock out soot. If you can prevent soot formation, now you can do things that are fairly inexpensive to control NOx. So that's been our approach. As the community well knows, you can definitely control soot formation by increasing fuel injection pressures, and that's what you see here. That's been a very effective strategy, been used for many years. Another strategy is oxygenating the fuel. By adding oxygen to the fuel, you can dramatically lower soot formation, but you have to add a lot of oxygen. You can see you have to get almost to 30 weight% oxygen. Biodiesel is about 11 weight% oxygen, neat biodiesel. So you're not going to get there simply by oxygenating the fuel. And you can't quite get there by increasing injection pressure. So what we decided to do was try to combine those two strategies. What if we increase injection pressure and we oxygenate the fuel? Well, it turns out you can do that, and you can prevent soot formation, and we call this linear lifted flame combustion. Basically now, in those products of rich combustion, you don't produce any soot. But you have to get the mixture at the liftoff length lean enough. And that lean enough threshold depends on the fuel, but conservatively, you want to get to an equivalence ratio at the liftoff length below about 2. Now, we tried to do this in the engine, and it turns out you can do it. We were unable to sustain high load, full load operation, but we were able to get to about 1/3 load by going to a very highly oxygenated fuel, so about 50 volume% of an oxygenate. And we had to go to some pretty high injection pressures, 240 MPa. So that didn't get us all the way to where we want to be, which is non-sitting combustion at full load. So we needed an improved approach. So where do you go? And this is pretty much where the community has been sort of stuck. So I started scratching my head and thinking about a long time ago, playing around in the lab with a Bunsen burner. Well, if you take the tube, you unscrew the tube from a Bunsen burner, and you light it, you get a big, tall, sooty flame. It's producing a lot of soot, and it's big and orange, and then you blow out that flame, screw on the tube, relight the Bunsen burner, and suddenly, magically, you have this really small little blue flame, and there's no more soot. Why can't we do that in a diesel engine? So that's the idea of ducted fuel injection. You put a little tube to enhance mixing and enhance entrainment, I believe, and thereby prevent soot formation. We don't really know yet how it works exactly. There are a lot of things going on. It's modifying the mixture, the thermal field, the velocity field. A lot of interconnected phenomena are happening. But one thing that we do know for sure is that it's very effective at eliminating soot. It enables us to achieve this LLFC, linear lifted flame combustion, that doesn't form soot over a pretty broad range of conditions. Also, because we ultimately want to use this strategy to control NOx by dilution, it has to be dilution tolerant. And we found out that it is. And like conventional diesel combustion, because this is kind of an enhancement of conventional diesel combustion, it's also tolerant to a wide variety of fuels. So it doesn't require an oxygenated fuel. An oxygenated fuel can really help. It further curtails soot production and enlarges the viable range, but it's not required. Here's some images from some early experiments that we did in a constant volume combustion vessel. On the left-hand column there, you see images of a free spray. The fuel injector tip is on the left side. and the fuel is spraying from the left to right. The right-hand column is ducted fuel injection at the same nominal conditions. These experiments were conducted with normal dodecane fuel, so it's not an oxygenated fuel. The ambient temperature is increasing as you go from bottom to top. The ambient temperatures are listed on the left-hand side of the free spray images. And so what you see is that what is shown here actually is the soot KL, soot absorbance, as determined by diffuse back illumination. So it's a quantitative soot diagnostic. But basically what you want to get from this is if you see reds and oranges and yellows, that's soot. And from the free spray, you're making a lot more soot than you are with DFI. In fact, for temperatures approximately 950 K or lower, the soot that's produced is below the detection limit of the diagnostic. You can't even see the soot. And even at higher temperatures, there's a substantial reduction in the amount of soot with ducted fuel injection. So, I mean, we're all engineers probably, right? And we have a healthy level of skepticism, so that's great, but can it work in an engine? So we started looking at I have an optical engine laboratory, so can we put this on the engine? Can we retrofit it? And it turns out that, yeah, you can put these ducts in there. They're pretty small. You know, they're only like 12 millimeters long, 2 millimeters inside diameter, so they're just little tubes. And it turns out they can fit in there in between the valves. You definitely don't want them to get hit by the actuating valves. And you could even put in longer ducts if you wanted by aligning them between the valves, as shown by those red dotted lines. So we did this, and we started out with just a 2-hole injector tip with 2 ducts, or actually with 1 duct, which is shown here. So there's sort of a schematic there on top that shows DFI on the right-hand side, and conventional diesel combustion on the left. And just below the cartoon, you can actually see an in-cylinder image of natural luminosity. So what you're seeing here at this camera gain, all you're seeing is soot incandescence. So if you, on the left side, you see a lot of incandescence from hot soot. Soot, you know, is just like a filament in an incandescent bulb. When it gets hot, it gives off light. So that's what you see here with the white signal on the left side. So conventional diesel combustion produces a lot of hot soot incandescence, and then this picture was taken at one instant. You know, we just had 1 duct on one side and no duct on the other side. So on the side with ducted fuel injection, we see little to no soot incandescence. So these are nominally exactly the same conditions, and we've really eliminated the soot. So I'm just going to give you a kind of a summary of these engine results. But if you really want to see the detailed results, please see the presentation by Christopher Nielsen, a coworker of mine, and he will be talking on Wednesday morning in the CI combustion and CI engines session. So here's the optical engine that we modified. It's a heavy-duty engine, 125 millimeter bore, 140 millimeter stroke. We looked at cylinder pressure, engine out emissions, regulated emissions, also oxygen and CO2. Fuel injection gives us the efficiency and the ignition delay. And our primary diagnostic is natural luminosity. This is a sensitive indicator of the presence and distribution of hot in-cylinder soot. The duct configuration, I want to talk about this a little bit more. Before I just showed a kind of a schematic of the duct. Now I'm showing a little bit more detail on the duct in this inset. So the key parameters, as you might imagine, are the duct diameter, which we kind of use this string to identify the different duct configurations. So D2 means it has a 2 millimeter diameter. L12, L, as you might imagine, is the length. So that's 12 millimeters long. And G is this standoff distance between the injector orifice exit and the inlet of the duct. So 3.8 millimeters. We found that the performance isn't super sensitive to that, but anyway, we list it. And then delta, we have found some actually pretty significant benefits to rounding the inlet of the duct and tapering the outlet. So anyway, that helps you, a little decoder for the duct configurations that you'll see. So Here is just a close-up, and you can see the duct mounting hardware around the injector tip. This is again the D2L12, so 2 millimeter diameter, 12 millimeters long, a standoff distance of 3 millimeters from the orifice exit. We're running, again, not an oxygenated fuel. This is a number 2 ultra-low sulfur diesel fuel. 30 weight percent aromatics, 9 weight percent 2-ring aromatics. So it's by no means a super clean fuel or anything. We ran at 2 different dilution levels to look at the dilution tolerance. And then engine speed and gross IMUP are shown there. You'll note the gross IMUP is rather low, but that's because we're using just this 2-hole injector tip. We just used 2 holes because we didn't want to be confused by jet-jet interactions, which can also can just make data interpretation more challenging. So we used a 2-hole tip, so that's one reason for lower load. And also you'll notice that the diameters of those injector orifices are rather small, only 108 microns. But the injection is long, so the injection duration would be characteristic of a high-load diesel operating condition. So we wanted to make sure that if we were going to make soot, that we would make it, that our injections would be long enough so that we'd be able to see it. So here are some movies. On the left-hand side of the block of 2 images you see there, the left side are, again, natural luminosity images, soot incandescence, and then on the right is the apparent heat release rate and SINL, which is spatially integrated natural luminosity. So it's like to add up all of the signal inside the piston bowl that we can see there. So the white dot, unfortunately I don't really have a good pointer, so but the white dot indicates the injector tip in the center of the image, and then the white circle is the piston bowl rim. On top is conventional diesel combustion, on the bottom is ducted fuel injection. I'll just go ahead and play the movies here so you can see. So now this is 2 ducts, as I showed you on the last slide, 2 ducts on the bottom, and you really don't see any soot incandescence again. And these data were acquired at 16 mole percent oxygen, so a decent level of dilution. So these would be conditions where, with conventional diesel combustion, as you can see, you're producing a lot of soot, and in fact, the amount of soot that you'd be producing would be maybe prohibitive for you to run here. But with DFI, we've really knocked down the soot tremendously. And that's what that says. So we've nearly achieved linear lifted flame combustion with this number 2 diesel fuel. So that's pretty encouraging. And these are conditions that would normally lead to unacceptable soot levels. So really, what we've done here is we have broken the soot-NOx trade-off, at least with dilution. And so you can see that a couple measure points, the squares are for conventional diesel combustion, and they show this typical soot-NOx trade-off curve. And then down, the blue circles show the soot-NOx response of DFI. So you can add dilution. I mean, DFI inherently gets rid of the soot, and then as you add dilution, the NOx levels go down. And it's unclear really yet where the dilution benefit ends. We think probably around 12%, where you start to lose combustion efficiency. And our more recent work, which I'll show you in just a minute, has shown us that oxygenated fuels provide even greater benefits. So again, the skeptics say, okay, yeah, sure, that's great, but what are the effects on other emissions and efficiency and heat release? Well, you saw a little bit on heat release on the last slide, but here's sort of a summary of where things go with ducted fuel injection. And what you see is really that it's primarily a soot reduction strategy. So soot is dramatically attenuated. And then the changes in the other emissions and efficiency are really quite small. So you can see indicated specific soot is down by almost a factor of 20, but indicated specific NOx, hydrocarbon, CO, and fuel conversion efficiency are not largely affected. 6.3% higher NOx, 25% lower hydrocarbons, a little bit higher carbon monoxide, and a little bit lower efficiency. That efficiency is that's a relatively low, relative number rather than an absolute. The absolute is less than 1 percentage point lower efficiency. If you look at the inset, you can see some differences between conventional diesel combustion, that's the black dashed line, and ducted fuel injection, which is the green dashed line. So DFI has a higher premix burn spike. We held start of combustion constant here. But another thing, DFI has a shorter burn duration, so this should ultimately help with efficiency. So now I had mentioned that oxygenated fuels benefit the performance even more than conventional diesel fuels. So we did this for the Department of Energy has this co-optimization of fuels and engines project, which many of you have probably heard about. So for co-optima, we looked at the effects of different oxygenated fuels. So we used a number 2 diesel fuel as our base fuel, and then we blended in 25% methyl decanoate, which is like a surrogate for biodiesel. It's a biodiesel like alkyl ester. We picked 25 volume percent because this is seems like something that's achievable in practice. I mean, you can buy B20 blends, which are 20 volume percent, in the market today, all around the US. So we thought that was realistic. And we also tried an ether with about twice as much oxygen per carbon to see whether we could actually get to LLFC with a little bit more oxygen in the molecule. Again, we're running two different dilution levels, but otherwise the operating conditions are pretty much the same as what I showed you before. So let's look at the results. Again, natural luminosity images looking up through a window in the piston. There's the fuel injector in the center, shown with the white dot. CFB, again, is the baseline diesel fuel, and this is conventional diesel combustion shown in this image. Over in the upper right of the image, you see GREL, that's the relative gain on the camera. So the camera gain is actually pretty low here. So we're producing a lot of soot. The low gain means there's a lot of signal. We don't have to turn up the camera. We don't have to make the camera very sensitive to see all this soot. In the center here, you can see a picture of DFI with the methyl decanoate, 25 volume percent biodiesel-like surrogate. And you can see around the injector tip, you can see the 2-duct assembly there. And it looks kind of comparable at first glance to the conventional diesel combustion until you look at the camera gain. So we had to turn up the camera gain by a factor of about 122 to see anything here. You can see at about maybe the 11 o'clock position in that MD25 image, you can see some saturation. That's from soot. But the rest of it would just look like a blue flame. This is very faint chemiluminescence for the most part, with a few little pockets of soot. So this represents a transition between conventional diesel combustion, where you're producing a lot of soot, and then leaner lifted flame combustion, where you're producing no soot. So basically, in this transition zone, you produce some soot, but it all burns out before the exhaust valves open. What we're actually trying to achieve is what you see here in this cycle with T25, where you just don't produce any soot. This is leaner lifted flame combustion. Again, the camera gain is up high. I'll go ahead and play the movie so you can see it. Conventional diesel combustion, pumping out lots of soot. The MD25 makes a little bit of soot, but it burns out before the exhaust valves open. And the T25, when you look at this, when you stand in the lab and you see this looking up through the piston window, it's just a blue flame. It's a kind of bluish pink flame. So there's really no soot. So that's pretty encouraging. And I think, as I started out, now we're back to, what was the objective? And I think we have really shown at least that this is a potential path toward the implementation of clean, sustainable, heavy and medium duty engines and fuels. So we maintain the inherently high efficiency. I think we can potentially improve the efficiency. I believe the efficiency loss is primarily because of heat transfer to the piston bowl, because effectively what you get with ducted fuel injections, you get like a little blowtorch right next to right next to the bull wall. And so what might be an optimal combustion chamber design for conventional diesel combustion is probably likely not optimal for ducted fuel injection. So anyway, it's a small efficiency loss that we've seen so far anyway. DFI is compatible with current diesel fuels, so there's no chicken and egg problem. This isn't like kinetically controlled combustion where you have to have some special fuel, and you know, energy companies are not going to want to produce these fuels that are so highly specified. It's fuel flexible, and the fuel that it needs is already out there. Now, that doesn't mean that we can't improve its performance with potential future diesel fuels. A lot of renewable fuels are oxygenated, and we have shown that these oxygenated fuels perform better with DFI. So that could provide a real market pull for more sustainable fuels. Lower emissions means maybe we can have smaller or less costly after treatment, or maybe, you know, probably with these ultra low NOx standards that we've been hearing about, at least maybe after treatment costs don't have to go up. And maybe we can hit the standards with an engine. It's easy to control. It's conceptually very simple. We're just putting some little tubes around the sprays. It's retrofittable. This is what we did in our experiments. So, you know, especially for large engines, you know, like maybe marine engines, locomotive engines, these could be retrofitted and you get benefits right away. And also it's scientifically distinct. So there's a whole different set of trade-offs between DFI, and actually these are well-known trade-offs because they're effectively the same trade-offs, many of the same trade-offs as you have with conventional diesel combustion. But they're quite a bit different from globally premixed strategies. So this provides stakeholders with a complementary technology path for meeting their objectives. So nothing is perfect, right? There are potential challenges with DFI. We saw it's going to have a higher premix burn spike, so we expect combustion noise to be higher, and we've measured it to be higher. Can we scale up to more ducts? We've only run 2 ducts so far. Can we go to 6 ducts? Will we be able to hit load? We're going to be testing that in the coming months. We've seen that DFI is pretty sensitive to the spray alignment with the duct. And so are we going to be able to achieve that? We were able to achieve it in our lab, but are you going to be able to achieve it in production? And are you going to be able to maintain that proper alignment over billions of injections over the life of the engine? How durable will it be? There are going to be deposits that form, thermal fatigue. You know, there are materials concerns that we just don't have enough hours. The first DFI engine tests occurred about 14 months ago in our engine, so this is brand new. Cold start, heat transfer, we believe is probably important. Cold duct during cold start might just exacerbate the problem. We don't know yet. I've talked about some of the challenges with efficiency and cyclic variability. We do see some cycles produce a lot of soot. Not more than the free spray, but they produce more soot. And some cycles produce no soot. And you can have conditions where, you know, 20% of the cycles produce soot, or 50% of the cycles, or none of 0% of the cycles. So, and we've actually seen that this cyclic variability extends to conventional diesel combustion as well. It's no bigger, I don't think, than conventional diesel combustion. It's just that with conventional diesel combustion, you're not so close to the sooting limit. I think there are differences from injection to injection in the spray characteristics. Anyway, we can talk about that later if you're interested, but I'll just summarize here. I wanted to leave some time for Q&A, so because that's where I can actually learn from you. So MCCI combustion is highly desirable. Of course, it's efficient, it's easy to control, has a lot of advantages. The historical challenge has been the soot-NOx trade-off. Our approach has been prevent the soot. If you can prevent the soot, now you don't have to worry about using dilution to control NOx. And that's what we did with ducted fuel injection. It's very effective at controlling the soot. It's still very early in the development process, but it dramatically lowers the soot. breaks long-standing soot-NOx trade-off, and it has some relatively minor effects on other emissions and efficiency. There are many questions remaining, of course, and we're planning experiments. And I'm encouraged to hear, as I talk to folks out in the audience, that they're actually starting to test ducted fuel injection in their own labs now. And I think that's great. And if you're interested, I'd be glad to help you learn from the mistakes that we've made. And I hope we can push this forward, because I do think it's really a path to clean, sustainable engines and fuels for the future. So with that, actually I want to acknowledge my coworkers. There have been a lot of people that have helped tremendously, and I'm just the lucky guy who gets to be up here and talk to you about this, but I've had help from a lot of interns. Christopher Nielsen's been with me since the very beginning, the very first proof of concept experiments where we fired the injection in the constant volume vessel and didn't see any soot, and we thought we'd had a camera malfunction. So him and Drummond Biles, Bonnie Uragan from Georgia Tech is currently with our group, and Ruth, Ryan Gemlick is a former postdoc. All these folks have been tremendously helpful. I'm very, very grateful to my colleagues, Scott Steen, Lyle Pickett, Julian Mannin, for letting us use their constant volume combustion vessel where we did the initial proof of concept experiments, and a lot of help from our technologists as well. So with that, I'll go back to the summary slide, and I'd be glad to take any questions. Thank you.
Great talk. We definitely have some time for a few questions. If anybody has any questions, please come on up to the microphone.
Hello there, my name is Ryan Mickelson, Environment and Climate Change Canada. Thank you for a wonderful presentation. The question I had for you is, if we see that these tests are continuing to be successful in the range of medium and heavy duty engines, what sort of challenges do you foresee in adapting this technology to more light duty applications?
For some reason with the acoustics, and I'm deaf in my left ear, I only caught the end of your question, and it's about light duty applications. Could you maybe please repeat the first part?
If we continue to see continued success in the application of this technology with medium and heavy duty engines, what challenges do you foresee in moving to more light duty applications?
Thank you. Yeah, so with light duty, I guess the primary things, as you can imagine, would be these ducts do need to have a decent length to diameter ratio. And if your diameter is going to be around 2 millimeters, what we found is that L over D needs to be sort of in the maybe 7 to 10 range, 6 to 10, somewhere in there. These ducts are going to have to be kind of long. And so with a light duty application, you probably are going to have to orient the ducts so that they go between the valves. And then you're probably stuck with just 4 ducts and a 4-hole tip. And no one's tested that. It may work great. 4 ducts with maybe 110 micron orifices like we've tested in the heavy duty engine, that might work just fine in light duty. But the other challenge is going to be, if you have like a re-entrant bowl design, you might start to run into potential interference between the duct and the bowl. And also, as I mentioned, you tend to get, it's like a blowtorch. It's more like a premixed, it's like a Bunsen flame. And if you put that Bunsen flame right next to the bowl wall, you can expect higher heat losses. So I think probably it's feasible for light duty, but it might require some combustion chamber modifications, piston redesign.
Thank you very much.
Thank you.
I might have one question for you, maybe. You showed where you could have, obviously, put multiple nozzles in together. Do you expect that they may all fight for air if you had sort of 6 or 8 of them together?
Yeah, that's a great question, Rob, and that's something that we're wondering ourselves, and I guess it just remains to be seen.
Find out.
Again, I think maybe with combustion chamber design, you might be able to help move the air in that direction if it does turn out to be a problem, but we'll see. Yeah. Stay tuned. We're going to do those experiments.
Great. Sounds great. Any other questions? Got one from Jim?
I'll ask one to keep it going, Chuck. Very nice talk. I want to relate this to the GM talk that Cherian gave yesterday that showed the ignition technology has to work under all of these applications. It's got to work. In his case, it was under light load and to promote various combustion modes. With the ducted fuel injection, and I know it's very early in the process, do you foresee, and you mentioned cold start might be an issue, but in terms of all of the different speeds and loads and all of the things that an engine has to do, are there weaknesses that you see or particular strengths that you see? So yeah, I'll leave it there.
Yeah, no, I get it, and I think it's a very good point, and that's something that we've been wondering as well. How is this going to work over the speed load range? So we do have some of our funding from Mike Weissmuller and the Capri Singh's Heavy Duty Advanced Combustion Engine program, is to look at the basically sensitivity to operating parameters. And I think from that research, we will have a much better answer to your question. But at this point, as you foresaw, it's just too early to tell.
Tim Johnson with Corning. Nice introduction there, Chuck. Have you looked at the distance of the duct from the injector? And I'm reminded of a paper that I saw with, I think it was Continental, in gasoline direct injection applications where they, as I envision it, I think they just extended the injector into the cylinder, kind of like a tube without any liftoff length. So what kind of sensitivities do you have to the proximity of the entrance of the tube to the exit of the injector?
Yeah, okay, that's a good question. Right, and that's one of the things that we struggled with initially while we were dialing everything in. What it looks like, and we haven't done exhaustive experiments, but what it appears to be is that it's not really sensitive to that gap, the distance between the injector orifice exit and the duct inlet. Performance is pretty insensitive within the range from about maybe less than 1 millimeter up to about 4 millimeters. But once you go a little bit too large, so like if the spray gets big enough so that it gets larger than the entrance to the duct, then you start to get big problems in performance. Performance degrades rapidly. So it's almost like, you know, there's no soot down in this bucket, and if you make the standoff distance too large, then soot goes up dramatically. And if you make the standoff distance too small, I'm not aware of this Continental paper, so I'd like to talk with you about that afterwards. But if you make the standoff distance too small, then you can't entrain in the air. And so then the soot goes up again. So it's a bucket with steep sides.
Okay. Let's thank Chuck one more time. Thank you very much.